Okay, now that we've talked a little bit about different types of errors and power and hypothesis testing, let's talk about some actual tests. One thing that I have shown you before that will still be really useful, going forward, even if you save this for other classes and things, and definitely will be useful to make sure you're using the right tests for your hypotheses, is this kind of decision tree where you need to think about the type of dependent variable you have and the type of independent variable you have, how many levels, and how your groups are assigned, and that determines for you what type of test you can run. You don't really get to choose the type of test. You choose the types of measurements and design that you have, and that indicates the test for you, basically. So we're going to talk about a few different ones of these for this video, and talk about what chi-squares are like, ANOVAs and t-tests are like. And remember that you have this resource to come back to should you ever need it. So let's start by talking about chi-square tests. They, in some ways, are one of the simpler tests we can run because they only involve dependent variables that are categorical, that are binary or having three or more categorical options. So things like did people engage in that behavior or not, or trying to think about low numbers of frequencies, basically. You can do chi-square tests with one variable, so without comparing two variables, and just say, is there some kind of imbalance within this one variable, and that's a goodness of fit test. What is usually more useful for experimental psychologists and researchers are the two variable tests of independence. So basically lining up two variable responses in a given participant and trying to say, are these independent or completely randomly distributed due to chance, or are they systematically related in some way? Like, is our IV related to our outcome, our binary or categorical DV? When you run a chi-square, like any test, it is going to give you a test statistic on a distribution. Some of the things we'll talk about, like t-tests and f-tests for ANOVAs, can be negative just if the difference is negative. Chi-squares, though, are never negative. The number that you're going to get is always going to be positive because it is a squared number. It can't be negative unless it's like imaginary numbers. So you'll always see positive numbers for chi-squares, and the way that this is calculated has to do with differences in observed and expected frequencies. So the expected frequencies are basically just that everything is equal and that you're going to get equal distributions of each variable according to the others. But if there's some imbalance there in what you've observed, then that's going to give you a bigger chi-square. So bigger chi-squares indicate more of a relationship between those variables. So just as an example, it's useful to think about these in what we call contingency tables, where you're kind of looking at how something is related by crossing them like this. So let's say we had two binary variables, people that graduated or failed to graduate, and if they were men or women. You want to be able to put a table together that lists all your data like this. So, if you look at the totals, that might tell you one story, but it probably doesn't necessarily tell you if there's some sort of systematic difference between men and women on this measure. So doing something to actually calculate if there is a statistical relationship between the two is very useful. Important to remember too that in these tables there's no overlap. Like, everybody that's in this square is not in this square, right? There are men that graduated and men that didn't. There are women that graduated and women that didn't, all separated in these cells. And these are just frequencies in here. They're counts of people, basically. So when you look at these types of things, it might be possible to say, like, well, it looks like, men that failed to graduate, it's kind of an even race here, and women seem to be really likely to graduate. There's probably some relationship here. But, by eyeballing tests, it's not really how we make our statistical decisions. We need to actually run our tests to make sure that we are noticing some sort of relationship. So if I... this one would be significant if we actually ran it. The example I have here on the next page is not a significant example. But if you ran a chi-square in SPSS, you would get some kind of output like this, basically. You know, on this one, it's not looking at graduation rates. It's between still male and female, and if people are not smokers or smokers. And when you run a chi-square, it's going to give you these results that show you the count, so like the observed number of people versus the, say, expected number of people, like I was talking about earlier. And it's going to run a test basically to see if these proportions are due to chance or not. So it gives you these summary statistics, and it also gives you the test statistic. The test statistic for a chi-square, like I said, is a chi-square. The Pearson chi-square, usually the one that people use. And I said higher numbers indicate a more reliable or significant difference there. This one is not very big. Usually chi-squares, you know, they need to be well over 1 to be significant. This one's not even a 0.5. So if you look at the p-value, which SPSS calls the asymptotic significance for some reason, because they rarely have things very clearly labeled in this program, unfortunately, you can see that it's not even close to 0.05, our usual threshold, right? It's at 0.5, so much, much higher. There seems to be no systematic difference between gender and whether someone is a smoker here. So the way that you would write this out is, I mean, when you write things out for your papers, you'll have example, kind of sample sentences to use, but this would say chi-square, parentheses, you'd put your degrees of freedom, 1, equals 0.440, and then you'd have your p-value of 0.507. So all the information you need is right here. Again, SPSS gives you lots and lots of information for more in-depth types of calculations, but you know, I'm going to try to show you the things that are actually relevant for you in this video, and Jenna and I will be doing that more again for other SPSS videos. It's always useful too to visually represent your data. I know that it can be a little confusing sometimes to know how to do that, so I want to tell you the types of more appropriate ways of doing that. When you have chi-square tests that are usually about ratios or percentages, it can be kind of confusing if you put them in terms of bar charts or histograms. So frequently the best way to do this is by showing pie charts, because these things are adding up to a whole, right? Unlike in a different type of experiment where you are you know, comparing separate groups that don't add up to a whole. Usually with chi-squares, there's some percentage that adds up to 100%. So it makes sense to show proportions of things when you're graphing those. So this also kind of drives home the point that, yeah, there's some difference here. Men seem to be more likely to be smokers than women, but it's not that big of a difference. So putting it visually can really underscore some of the things that might be more abstract when you're showing things statistically. Okay. So moving to some type of test that a lot of you are going to be doing for your projects, t-tests. We know that these are tests where we're looking at differences between groups. Again, these can be independent groups that are randomly assigned or pre-existing in some way, but they're mutually exclusive, or they can be the same people being measured again and again in a repeated measures or within subject's design. But essentially in a t-test, you are coming up with a mean for each of these groups or each of these measurement periods and trying to compare them to the other period to see if there is a likelihood that those differences are significant or not due to chance. So let's say you had you know, some outcome variable, it doesn't really matter what it is, in two different groups. If you ran a t-test in SPSS between your different experimental groups on your outcome, like some intelligence measure or something, this is the type of output that SPSS would give you. It would show you the means and standard deviations very helpfully for these different groups that you would have. And you know, you don't need to usually for APA formatting, you round to the nearest hundredths place, so you don't need to include all this stuff, but it's useful to have all of it. So this is kind of the summary descriptive statistics for each group, and then it gives you the actual inferential statistics down here. For a t-test, it's really important to note that this f-test over here is not your test about whether your groups are different. This is something separate. Your t-test is over here. Under where it says T, obviously, and it gives you your significance level and your degrees of freedom. what this is over here, this Levene's test for equality of variance, is like it's a check to make sure that your data match the assumptions of a t-test. So for a t-test to work properly, the variances between your different experimental groups need to be very comparable. If you have a significant f-test, that means they're not comparable and you need to use some kind of correction there. So if your f-test is not significant, that's a good thing, essentially, that you didn't violate that assumption, and you would just use this first line of the SPSS output. But if this one is significant, then that indicates to you that this is the appropriate line below, that there is some kind of correction that needs to be made in the degrees of freedom for your test to work properly. So the f-test is telling you which one of these lines to look at. If it's not significant, use the top. That's usually going to be the case. But if it is significant and there's a correction needed, you use the bottom. And remember what I said previously about distributions and having a directional hypothesis, and how this significance level is two-tailed here. Because it's two-tailed, if you had a directional hypothesis, if you had said, I expect group 2 to have a higher mean than group 1, then that's directional. You're not ambivalent or agnostic about the different direction. So if you have a directional hypothesis, you are actually testing a one-tailed test, and you need to cut this p-value in half. So it would be more like 0.415 or 0.0415 or something. So you would tell your readers, t, parentheses, your degrees of freedom of 19 equals 1.83, and your p-value of a little over 0.4. So this would have been a significant difference here. The way those degrees of freedom are calculated, it's important to note, are it's n minus 2. So if we go back to that SPSS output, you had 21 people in the sample, 10 plus 20 or 10 plus 11 is 21. N minus 2, so your entire sample minus 2, 21 minus 2 is 19. So that's where this 19 comes from. So it's important to remember you should always have your t-value, your degrees of freedom, your p-value, and when you're talking about your groups, you need to give those means and standard deviations that you see up here. It's also really important to include effect sizes, which is something that I'm not going to have you do for this class because it's a little more calculation than I think is necessary for you to really learn at this point, but I want you to be aware conceptually of what they are, at least. Effect sizes are, how meaningful our effects are in a lot of ways, how big they are. To calculate an effect size for a mean difference, you take the mean differences for each group. So mean of group 1 minus mean of group 2, that gives you a difference here in the numerator, and you divide it by like a combined value for their standard deviation. So this is the calculation for how you do that. I'm not going to test you on these types of equations, obviously, but calculating this whole thing is the denominator, basically. So what it gets down to is it's comparing this mean difference to the average or pooled standard deviation. So it's basically saying, is the difference between these two groups bigger or smaller than the difference within these different groups? So if you had a mean difference that was bigger than this, your number would be bigger than 1, essentially. So the way you look at these things, essentially, is if you have a mean difference that's as big as a standard deviation, that's a pretty big effect. So if your D is 1, that's usually considered pretty big in the social sciences. So anything over 0.8 we might consider a large effect, according to these kind of guidelines from a researcher named Cohen in the 70s. And you can see here medium and small size effects as well. Again, I'm not going to have you do this for this class, but it's important to note that these are there's a movement towards including effect sizes rather than just relying on p-values, because again, if we're just using p-values, that can be a little misleading, and the actual sizes of effects in a standardized way, like by standard deviations, might be a better way to look at those things. Not just for chi-squares do we want to visually represent things, it's also important to show these for, different groups we're comparing in t-tests and ANOVAs. For a t-test, you want to do this with a histogram or bar chart to show these differences. You always want to have your groups on the x-axis on the bottom horizontal one, and your dependent variable on your y-axis, so higher scores being higher up on the y-axis. And you always also want to include error bars that show your standard deviations, so people can kind of interpret what these types of differences mean. If these error bars were really small, this would be a lot more meaningful difference than if they were kind of on the bigger side, like this. It's also important just to think for a second about what this axis means here. You notice that this goes from 0 to 30, and it kind of encompasses all of this difference here. It includes all the error bars. Somebody could cut this off right here and not really show you everything. So it's important to be pretty straightforward about what your axis is, and not truncate your scale too much and make your differences look bigger than they are just by using a smaller proportion of your scale. Okay, so when you have more than two independent variables, t-tests are for only two group comparisons. ANOVAs are for more than two groups. It's important also to note that for most of your projects, you're not doing interactions between different variables. You're just looking at the differences between, let's say 3 or 4 different conditions. When you are only comparing one independent variable like that, you call an ANOVA a one-way ANOVA. When you're using, 2 and you're interacting them, you might call it a two-way ANOVA. And if you have 3, a three-way ANOVA, and so on and so forth. But for our purposes, we pretty much will focus on one-way ANOVAs until we get to complex experimental designs in a few weeks. ANOVA is short for kind of a cute little phrase for analysis of variance. It's just looking basically at how much variance there is between those groups and using that to say something about the mean differences. The test statistic for an ANOVA is an F statistic. It uses a different distribution than the T distribution, which is kind of close to normal. The F looks a little bit different. And the degrees of freedom are different because you have to describe the number of groups as well as the number of participants. So K represents the number of groups, N is the total number of participants. So if you have a one-way ANOVA with 2 groups, that's 2 minus 1. If you have a three-way ANOVA, a one-way ANOVA with 3 different groups, that'd be 3 groups minus 1. So that affects that first number here. And if you had like 300 participants minus 2 groups, then you'd have 288 right here, right? And that comes out in the SPSS output. One-way ANOVAs, you can use them for independent groups or repeated measures designs, and it's important, I think, to note something special about the hypotheses for ANOVA as well. The null hypothesis for ANOVA doesn't just mean, that there's no difference. It specifically means there's no difference between any of the groups. None of the 3 or however many groups differs from any of the other groups at all. And the alternative hypothesis for an ANOVA by default is that 2 of the groups somewhere differ. But that finding itself doesn't tell you exactly which one. You need to do follow-up tests to actually see where that difference is. So if you had groups A, B, and C, an alternative hypothesis that's significant, it just tells you that some of them are different. It might be A and B, it might be A and C, it might be B and C, it might be all 3. You don't really know. You just know from a significant F statistic that there's some difference there that you need to account for. The effect size for ANOVA, you generally are going to use something called eta squared that talks about the proportion of variance that your independent variable accounts for. The formula for this is a little bit different, but it kind of approximates what is going on with lots of other effect sizes, that you're looking at the sum of squared differences between groups compared to the total sum of squared differences in your study. So another way to think about this might be the variation between your different independent variable conditions divided by the variation in every possible source in your study. So it's really comparing the difference between your groups to everything else. But frequently that means that this is going to be a pretty small proportion, maybe around like 0.1 or something in a lot of models. So this eta squared is talking about the whole test that you're doing. But frequently people, when they're comparing two of the groups in follow-up tests of ANOVAs, they'll still use Cohen's d to make those different comparisons between groups. So that last formula I talked about still matters here. And there are other, there are lots and lots of different effect sizes. People have different opinions about them. Sometimes you might want to take different types of error and sample sizes into account, so there are other options like an omega squared. Okay, when you run an ANOVA and SPSS, the output's going to look a little bit different. It's going to tell you, the groups, how big they are, how many subjects are in each group, the score that people are getting on average in those groups, and how much they're deviating, and then a lot of other stuff that is useful in its own way, but maybe less appropriate for our class at this point when you're still trying to get a basic handle on things. So these are the descriptive statistics. The ANOVA table also gives you the test statistics, right? And those degrees of freedom I talked about earlier, remember k minus 1, so we have 3 groups here. 3 minus 1 is 2, that's where this 2 comes from, so the between groups degrees of freedom. And then we have 46 total participants in 3 groups. 46 minus 3 is 43. So your degrees of freedom for this would be 2, 43. So you'd have f, parentheses 2, 43 equals 15.34 is your f statistic. And the significance level here for this particular test is 0.000. It's important to note that a significance level is never actually 0. It's kind of an unfortunate thing that SPSS chooses, or the designers choose to represent it as this. But if you were to click on this in SPSS, it would give you a number that's, maybe 0.000004579 or something. There's never a 0 chance that your results are due to chance. So if you get a 0 result on your hypothesis test for your study, you should not write it as 0.000. You should write it as less than 0.001. And then that indicates that you're recognizing that that there's some kind of chance there that your results are not due to 0. The way that you graph ANOVA results, just like with a t-test, you would use a bar chart or histogram to represent these things with the groups on the x-axis and the dependent variable on the y-axis, including those standard error bars. To wrap up this video before I go on to talk about some exercises in the next one, it's important to think about your data. Again, we've talked about this with descriptive statistics. You need to double check things and make sure your data looks the way that you expect it to. It's shaped the way you expect it to. It varies how you expected. It's, normally distributed. It's not multimodal in some weird way, and that it conforms to the assumptions of the test that you plan to run. So check your data out before you run your tests, and then you'll avoid a lot of work and problems later if you find out that something was violated. All right, thank you, and I will be back in a minute for some exercises and then a little summary of something about probability.